So, hello. Now we are going to have the mini course of Mario Garcia Fernandez from ICMAT Madrid. He's going to talk to us about vertex algebras and special holonomy on quadratic Lie algebras. Thanks, Mario.
Okay, so thank you. Do you hear me here? Yeah. So thank you very much. I would like to thank the organizers for the kind invitation to give this mini course. It's always a pleasure to be back in Rio. So I changed slightly my title because I realized that the audience is quite diverse and maybe something more algebraic would accommodate better part of the audience. So what I'm going to tell you about is maybe a bit basic today, but the idea is to do geometry in some algebraic object, which is a quadratic Lie algebra, and study some moduli spaces of solutions of some equations in a quadratic Lie algebra, and next day try to show that if you have a solution of that equations, then some interesting vertex algebra representations arise. So as a sake for the motivation, let me start with, so you have a Riemannian manifold, which I'm going to assume is a spin, and suppose that you have a parallel spinor. For the Levi-Civita connection. So the Levi-Civita connection, the spin connection associated to the Levi-Civita connection annihilates a spinor. Then the holonomy of the metric automatically reduces to the stabilizer of the spinor inside SON. And furthermore, there is a nice formula which tells you that the reach is 0. This type of geometry is our biggest source of Riemannian metrics with vanishing Ricci tensor that we have up to date. So examples are Calabi-Yau metrics, hyperkähler metrics, quaternionic Kähler metrics, etc. So there is a construction by Malikov, Sheshman, and Weintraub, which tells you that whenever you have a manifold, you can do this in any category, in the algebraic or smooth here, there is a suitable sheaf of vertex algebras, which I will explain what they are in the next lecture. And there is a lot of literature, in particular from people here at IMPA. So there is work by Helwani and collaborators, Densby, Seksenik, Sabsin, Ekstrand, etc., which tells you how to construct spatial embeddings of suitable vertex algebras in the cohomology of this sheaf. So spatial embeddings. Of suitable vertex algebras associated to parallel spinors in the cohomology of this sheaf. So these are just words by now, but this is the overall motivation of my talk. Interesting applications of this are to the construction of topological invariants, or an upshot of this is the construction of topological invariants which arise as some sort of character associated to how this cohomology splits into reducible representations for this. In particular, one example of this is the elliptic genus of a Calabi-Yau manifold by work by Borisov and Likover. And despite this, I mean, on top of these mathematical applications, people have been interested in this over the years for potential applications to mirror symmetry. There is a proposal by Borisov which tells you how to understand suitable aspects of mirror symmetry using vertex algebras via this type of construction, and more recently, also to holography in work by Witten. Okay, so this is the last time you are going to hear about manifolds in my talk today. I'm going to go now to a more algebraic setup, which is motivated by this picture, but is fairly simple. So I hope it accommodates everyone in the room. So my first lecture of the mini course is entitled, guess what? Geometry in algebra. So you can imagine the title of my second talk. And the type of algebras where I'm going to do geometry is very simple, are just quadratic Lie algebras. So I'm going to fix G with a bracket and pairing a quadratic Lie algebra. So let me remind you what this is. Hopefully everyone knows here what a Lie algebra is. If not, you can complain and I explain it, no problem. So it's a vector space with a skew-symmetric bracket which satisfies the Jacobi identity. So this is a Lie algebra, which for me, in these lectures, is going to be over the real numbers, but you can consider it over different fields. And this pairing is just a symmetric bilinear form. Which is preserved by the bracket in the sense that ABC plus BC is 0. Okay? So let me give you one example, which is the motivating example. So if you are a geometer, this is the type of example that you should think of. The typical example that you can think of is take K a Lie algebra. For example, a compact Lie algebra, and fix a pairing as before, but now in the Lie algebra of K, also invariant. And then take your G to be K plus K dual with a natural bracket, which is given as follows. You define H, which is an element in lambda 3 of K dual, which is defined by the Cartan 3 form to this bilinear form. H ABC equals, I should have written different letters, but anyway, is ABC. And now you define a bracket which has this form, which is so B plus alpha W plus eta is just the Lie bracket. So this V is going to be in K. This alpha is going to be in K dual. And similarly for the other one. So this is just the bracket of B W in K minus this should be eta V bracket, or if you want add, plus alpha W bracket plus the contraction of the 3 form with B and W. And you can check that this satisfies the Jacobi identity. And furthermore, there is a natural pairing, which is invariant under this bracket, which is given by duality, which is given by alpha of B. Okay. So if you like geometry, then you can think of the picture happening on a compact Lie group, whose Lie algebra is going to be little k. And then you can think of all these things I'm going to say as doing so-called generalized geometry a la Hitchin on Tk plus T star k, twisted by the Cartan 3 form on the Lie group. Okay, so I want to do geometry on this quadratic Lie algebra. So the first thing is to tell you what is a metric. And I will actually have to tell you a bit more. You need some more ingredients for doing geometry. Okay, before that, maybe a bit of motivation. This is like the one aspect of these quadratic Lie algebras, which can be thought of as, if you heard of this before, as current algebroids over a point. So quadratic Lie algebras can be thought of, on the one hand, as current algebroids over a point. But also, some people here like supermanifolds, and via this Several-Reutenberg correspondence, they can be also thought of as symplectic supermanifolds. Again, over a point with something called homological vector field. So maybe this helps to have some ideas on what is going on. Okay, so given a quadratic Lie algebra, I define the following objects: a generalized metric. I'm not going to mention this generalized anymore, so everything is going to be generalized. But anyway, a generalized metric, sorry, on this quadratic Lie algebra is going to be G, some endomorphism of the Lie algebra with no compatibility with the bracket whatsoever, but satisfying that the G squared equals to the identity and that this is orthogonal with respect to the pairing. And I need another ingredient. Okay, first, if you have a generalized metric, then you have an endomorphism which is equal to the identity, so you can decompose the Lie algebra as B plus B minus, where here G acts as identity and here G acts as minus identity. And I'm going to require further, not only this, I'm going to require further that this thing is non-degenerate. It's a non-degenerate metric, non-degenerate pairing. Which this means is that when I restrict the pairing to B plus or B minus, this gives me a non-degenerate tensor. So this is the analog of a metric in this setup. Interesting cases, and I will go back to that, are, for example, when the metric restricted to B plus is positive definite. But in part of the theory goes through without any assumptions. And the other ingredient that I need is something called a divergence, which in this setup is simply an element in the dual of the Lie algebra, which in this geometric setup, I want to think of as some sort of differential operator acting on sections of T plus T star. Okay, but here is just going to be an element in the dual, but it's going to play an important role. So the first thing you do in Riemannian geometry is to construct connections and curvature. So let me tell you what a connection is in this setup. A connection is some map going from G to G dual tensor G. which is compatible with the pairing. And here, what I mean is that when I put the subscript, I mean that I'm contracting the D with the G dual. So I'm thinking of this as a covariant derivative. I'm taking derivatives. So another way of thinking of this, because of this constraint, is that D is an element in G dual tensor lambda 2G. I mean, here I'm identifying G with the dual using the pairing, but it's fine. And I'm going to say that a connection is compatible with a generalized metric G if this commutator is 0. Okay. This is the same as saying that dA is going to preserve B plus and B minus. So this condition, what this tells me is that my D is going to split into 4 operators. One which takes derivatives of plus with respect to plus, one which takes derivatives of plus with respect to minus, minus with respect to plus, and minus with respect to minus. So the basic example you should think of is very simple, and it uses just projections. So the example you should think of is, let's denote if I have A in G and I have a generalized metric, I can decompose uniquely this as A plus plus A minus. This is in B plus, and this is in B minus. I'm going to use this notation all the time. And now I can define a generalized connection, which is given by simply taking A minus B plus 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 A plus B minus minus. So given a connection, I have two. Given D, I have two natural quantities associated to this. I can define, on the one hand, I can define a divergence associated to the connection, which is phi D equals to, phi D acting on A, which is minus trace of dA. And I can also define torsion, and this is a definition by Alessia and Chu. Alessia and Chu, which is an element in the third x0 power of G, which is defined as follows. So just copy the definition of torsion on a manifold using the bracket. And then you do this ugly or funny looking correction. And you can check that with the given actions, this is an element in lambda 3. And then one structural property of this is that define this space of connections, D0G phi, for a given metric and divergence to be the space of these which are G compatible and have a torsion and have divergence equals to phi. Then this space is non-empty. So there are compatible connections with fixed divergence. This is non-empty, but it's not a point. So there are many, these are like Levi-Civita connections, and there are many. Yeah?
This equation GAAG equals the sum of brackets. Where does this come from?
This?
Yeah.
I'm going to explain now.
Oh, okay.
This is canonically part of any connection living in this space. Furthermore, for all the Levi-Civita connection, in the sense that it has no torsion and has fixed divergence, if I take derivatives with respect to minus of plus, this is precisely A minus B plus plus. So this thing here. And if I take derivatives of plus with respect to minus, this is precisely A plus minus minus. So these bits are canonical. And the only thing that, the only freedom that I have when I deal with these connections in a quadratic Lie algebra is coming from these two operators. The fact that this is non-empty is a constructive proof. I mean, you just write down a formula. And if someone is curious, I can show you, but let me not go for that. So, okay, so we have a notion of metric and connection, and I want to introduce some equations which tell me that my metric and divergence has reduced holonomy. And I'm going to do that using spinors. So given a metric G, consider the Clifford algebra of B plus, which recall is defined by the relation A plus equals A plus A plus. So it's the tensor algebra quotiented by this relation for A plus and B plus. And we fix an irreducible representation for Clifford, which I'm going to denote H plus. And then, given D in my space of torsion-free Levi-Civita connections with fixed divergence, I can define two operators. The first operator is something that I'm going to denote like this. It's like the spin connection associated to my generalized, to my connection, sorry. It's an element in V minus dual tensor endomorphisms of S plus. And this is just given by the fact that D minus plus is naturally an element in B minus dual tensor lambda to B plus, and this sits inside here naturally. And my second operator is some sort of Dirac operator. Is D plus slash, going from S plus to S plus, and takes a spinor eta and sends it to the following quantity: sum from j equals 1 up to the dimension of B plus Ej plus Clifford product T Ej plus eta. And here I should write this thing, but anyway, this is clear. Okay, so this is like the action of a Dirac operator. And then the lemma is that these two quantities, these two operators are well defined independently of choices in here. So lemma and d s plus and d slash plus are independent of choices of d in d0 and g5. So in particular, they only depend on the choice of metric and divergence. So with this, I can tell you what is a special holonomy metric in this context, which is given by the following definition. So definition, a tuple given by a metric, a divergence, and a spinor satisfies the Killing-Spinor equations which I'm going to denote KSE, if ds plus eta is 0. So when I take derivative with respect to minus of eta is 0, did I put the minus? Yes. And the other one is this is also annihilated by the Dirac. Yes? S plus is an irreducible representation for Clifford. Okay? So these equations are reminiscent of equations which appear in the physics literature. In the geometric setup that I mentioned before, when you have the tangent plus the cotangent of a compactly group, this will be called the Gravitino equation. And this will be called the Dilatino equation. So why are we interested in this? Let me tell you two motivations for this. So, the expectation, the general expectation is the following. One is that the modular space of solutions is an interesting object. And here I mean solutions of the Killing-Spinor equations modulo the natural action of G. So this should have a special metric. And we'll see some examples later. And second, that given a solution, there should exist a vertex algebra embedding for some special type of vertex algebra associated to the solution into the Kac-Moody affinization of G. Okay? This is the motivation. So regarding to, we have in this paper I mentioned at the beginning with Luis Alvarez Consul and Andoni de Arriba de la Era, we managed to realize this in the case that the dimension of B plus is even dimensional. And furthermore, the metric is positive definite. And in recent work with Matteo Galdeano and Andoni de Arriba, we have done this also for the case that the dimension of B plus is 7 dimensions in relation to the satisfiability of vertex algebra. And a remark, maybe some people here are interested in this, is that in the geometric setup, in the case tk plus t star k, the expectation is that this moduli space is a two-stack. This is here is just I'm quoting it by Ali algebra, but in this case should be a two-stack. With some special geometry on it. So people like Enrique Bernstein and Daniela Alvarez are studying this type of thing. Okay, so how do we find, well, firstly, if this makes sense, if this is a well-defined notion of a special holonomy in this setup, this should imply some vanishing of curvature. Yes?
Sorry, the space M, so it's a quotient by G?
Yeah.
What's the action of G?
Yeah, I mean, there is a natural action in this tuple, right? Because, I mean, you can think of the group, a simply connected group integrating G, and it will be like act on the space. This is the space of endomorphisms. This is just the dual. Okay, so there is a natural action. So first, I want to briefly show you that these equations imply some vanishing of curvature in some sense. And also, this will naturally lead us to a machinery or a proposal for finding solutions, which is using some geometric flow. Okay, so I'm going to define some objects which I will call Ricci tensors. So associated to G phi, there are well-defined Ricci tensors Ricci plus is going to be an element in B minus tensor B plus, where B plus, B minus is the decomposition of the given by the metric. So G acts on as identity on B plus and as minus identity on B minus. And similarly, it's going to be Ricci minus in B plus tensor B minus. I'm here, and I'm going to write this if these objects were in elements in the dual, but everything is identified because I have non-degenerate pairings. So what is, for example, Ricci plus? Of course, this is depending on G and phi of A minus B plus is going to be the trace of the endomorphism which takes C plus to RD A minus, no, C, sorry, RD C plus A minus B plus, where RD is defined as like the standard curvature. RD ABC is just the commutator of dA dB acting on C minus D of the commutator of AB acting on C. Okay, and the minus is defined in a similar fashion, changing plus by minus. Okay, so this is not obvious, but so the lemma what says is that if I choose any D in the space of connections with fixed divergence and zero torsion, this quantity doesn't depend on choices. Okay, it's well defined. And now one comment about this is that in the geometric setup, when you have the Lie algebra coming from Tk plus T star k, the vanishing of in geometric setup the vanishing of the Ricci plus, for example, corresponds to the equations of motion of some physical theory. This corresponds to the equations of motion of some physical theory, which is a supergravity theory on a Lie group. Supergravity theory. And one can write this down very explicitly, but let me not go for that. So the result now is that if you have a solution of the Killing-Spinor equations, then the Ricci plus is 0. And furthermore, if the divergence understood as an element in the Lie algebra instead of the dual, if the divergence fixes G, then also the other Ricci vanishes. So the two Riccis are essentially equivalent. So how do you prove this thing? Well, there is a very nice formula. It was discovered by a physicist, and which I took the time to prove rigorously, which is the following. So the proof is a very simple formula using spinors. It tells you that you take the Ricci plus of G, let me remove this thing, and contract it with A minus, and act on a spinor. So this is an element in B plus, right? So I can act on a spinor. This is the same as the commutator of the Dirac operator and the A minus S plus. Minus ds plus of d minus, d plus A minus acting on the spinor. So if we have a solution of the Killing-Spinor equations, d of f plus on the minus annihilates the spinor, and both this and this annihilate the spinor, and that's it. Yes? Yeah, I'm going to all the time, because I have non-degenerate pairings, I'm going to all the time identify the elements with the elements in the dual, okay, without mentioning. And the other observation is that if phi fixes G, I will call this, this is like it's like a killing field, right? It's a vector which annihilates G, the metric. Then what happens is that one has a very nice formula which relates the plus and the minus Riccis. B plus A minus. And that's it. Okay, so this finishes the proof. Why I'm telling you this? Well, one is for the sake of motivating the fact that this is a special holonomy. So in this setup, there is a natural notion of curvature, at least of Ricci, not of curvature, but of Ricci. And these Killing-Spinor equations imply the vanishing of the Ricci. The other reason why I'm telling you this is, okay, these equations are nice, but where can you find solutions of this? This proof suggests a way of finding solutions, which is via a geometric flow. So generalized Ricci flow is a way of producing solutions of these equations, which is taking a family of metrics, GT, and evolving by gt minus 1 partial tgt equals, and usually you put, in the theory of Ricci flow, you put here a minus. So minus Ricci plus minus Ricci minus. So to understand this, think of which type of object this is. So the Ricci plus, I can think of it as something that goes from the minus to the plus. So as an homomorphism from B plus to minus. And this other part, I can also think of it as an homomorphism from B minus to plus. But this is precisely the place where these variations live, right? Because G squared is the identity. So if I take a variation, this quantity is going to satisfy, if I call this G dot is going to commute, it's going to satisfy that G dot G plus G dot is 0. So it's going to anti-commute with G, which is telling you that it's exchanging the B plus with the B minus and the B minus with the B plus. Because G restricted to B plus is the identity, G restricted to B minus is minus the identity. Okay? So recall that G is identity on B plus minus identity on B minus. So this is a mini course, so I should give you some exercises. This is not really an exercise, it's a problem, which I don't know how to solve. I think it's an interesting problem. Prove short time existence for this evolution equation for general Ricci flow. And the second is that if we have a solution of the Killing-Spinner equations, we have a metric and a divergence which have vanishing Ricci. Okay? So a way of trying to find solutions of the Killing-Spinner equations is to find a metric which has vanishing Ricci. The second problem is assuming that you have a solution, exists solution of Killing-Spinner equations, then prove long time existence and convergence. Prove long time existence and convergence. There is, I'm not sure if I'm going too fast, or someone should have complained from the fact that here I have defined the Ricci using a divergence, and here apparently there is no divergence. What happens? So the natural thing to do here is to take the Ricci corresponding to the zero divergence. Okay? And similarly as in the theory for Ricci flow, that vector fields appear in limits as solitons, a natural divergence should appear in order to prove the long time existence of the flow in the process of killing spinors. In the geometric setup again, for compact even dimensionally groups, I have been able to prove this jointly with Straits. So this is a theorem with Straits and Jordan. Using PDE techniques. And here what I'm proposing is something simpler. This is really a system of 4D, okay? So try to prove short time existence and also long time existence and convergence in this simple case of the quadratic Lie algebra, okay? And this is just a system of 4D. I'm not claiming that this is a vanilla problem. This is not, I didn't state this as an exercise. This is really a problem. Okay, so this is one machinery in order to prove that there are solutions of the Killing-Spinor equations. Another motivation for considering this flow is that in the geometric situation, again, this flow, physicists know it in a different form or by a different name. So for physicists, the generalized Ricci flow is the renormalization group flow of a two-dimensional sigma model with target the group K, with target K. So this is a compact Lie group, and my quadratic Lie algebra is going to be K plus K duo, as in the example at the beginning. Okay, so this flow is very natural. It comes from renormalizing a sigma model. So if you want, by studying how a two-dimensional sigma model behaves under change of scale. And physicists have been considering this for a long time. Here I'm just like axiomatizing this in terms of, or in the setup of quadratic Lie algebras. In particular, from a physical point of view, it should tell you that if you have a fixed point of the flow, somehow you should be able to construct a conformality theory. Okay?
Sorry, could you say the relationship between Ricci flow and solutions including spin equation?
Yeah, it's a bit vague, but what I'm saying is that if I have a solution of the Killing-Spinor equations, then I have a vanishing Ricci metric with divergence. And in geometry, we know that if you have a special holonomy metrics, Ricci flow converges to this metric, maybe up to gauge, in good cases, or maybe to solitons or things like that. Okay. So the expectation is that if you run this for any metric on a quadratic Lie algebra which admits solution of the Killing-Spinor equations, then up to maybe up to gauge, this should converge to a solution of the Killing-Spinor equations. Yes.
So then you expect something like for SU3 when you have these solitons where each flow converges together, something like that?
Yeah, it should be something like that, but I mean.
Like you have with 3 you have a nice picture, polytopu and solitons.
Yes, I mean.
And then we can keep N as the polytopu in this case, where the flow, this flow is inside of N.
I mean, the geometric way of thinking of the flow is thinking as a flow on a compact Lie group, okay? The quadratic Lie algebra is going to be K plus K duo. And when you write down what a metric is in this setup, it's going to be a left invariant metric on K and a free form. And you have some equations for this metric and that free form. So if you want to know the basics about this, you can, jointly with Streets, we wrote a book about general Ricci flow, and you can actually find a nice example where we prove long-time existence and convergence of this on the case SU2, which is at the 3-sphere. And you observe that this flow, when you write it geometrically, is some extension of Ricci flow, and it has a very different behavior. Ricci flow collapses the 3-sphere to a point in finite time. This thing has long-time existence and convergence, depending on the choice of free form. So it's a different object.
So this flow is presumably on a metric, so the divergence operator and the spinor are fixed?
Sorry, can you say?
So this is a flow only on a metric, so the divergence?
This is a flow only on the metric. I'm saying that when you consider this equation, you should think of as the divergence to be 0. And the expectation is that in order to prove convergence, you should do some sort of gauging, time-dependent gauging. And this is how, I mean, the fixed points are going to be our long time. I mean, the limits of long-time solutions of the flow are going to be solitons. And the solitons depend naturally on vector fields. And the analog of this is the divergence. Yeah, I didn't. For some reason, I didn't say what a general metric is. Okay, so how much time do I have? How much time do I have? Until 1. Okay. Okay. I think I'm running a lot. Let me explain one thing here. In this geometric situation, so I have a compact Lie group. And then I take this quadratic Lie algebra K plus K duo. What is a generalized metric in this setup? a generalized metric is going to be generically at least, of the following form. So first, this is just a decomposition of G into B plus plus B minus, such that the pairing restricted to B plus minus is non-degenerate. Assume, furthermore, that this is, for simplicity, that this is positive. So it's going to be negative in the minus. And then my generalized metric can be written as follows. It's going to be e to the b x plus gx, where x is an element in K, so it rises as a graph. My G is a symmetric tensor on K. And the B is a two-form on K. So this is the usual picture about generalized metrics in generalized geometry. And here, if we have fixed H0 to be the Cartan 3 form on the group, and this is the appearing in K, not in G. So you fix the killing form. And this is going to be invariant, and therefore it's going to be closed. Then, associated to any generalized metric, you have also a 3 form, which is H0 plus dB. So if you take the time of writing down this flow explicitly, it's going to be a flow for the metric G, which you can think of as a left invariant metric on the compactly group, and for a 2 form B. And alternatively, you can think of it as a flow for the metric G and for the 3 form H. Essentially, the metric evolves by some deformation of Ricci flow. The 3 form evolves essentially by the Laplacian, I mean, by the heat flow. But you can describe everything like algebraically as I did. Okay. So I didn't give you any examples, so let me go for examples. But for that, I need to specify a little bit more, right? This is too general. So let me specify to the case where B plus is even dimensional. So this is the case that the dimension of B plus is 2n. In this case, we know that a complex pure spinor eta on B plus is equivalent to a decomposition of the complexification into Lagrangian subspaces, which I'm going to denote L plus L bar. So what is L? Are the elements in V plus tensor C, which annihilate the spinor. And these two are going to be mutually dual and Lagrangian. And this means that this guy is the conjugate of this. Okay? So whenever I have a complex pure spinor, I can think of as a complex structure on B plus. So I can define J eta, an endomorphism of B plus, which on the complexification is just I identity L minus I identity L bar. And in this setup, we can write down a much nicer formula or expression for the killing spinor equations, which is actually the type of formulas or the type of expressions that you use in the vertex algebra calculations that will follow next day. So in this setup, So if you have a solution of the Killing-Spinor equations, solution of Killing-Spinor equations as before with eta pure, then, and this is really an if and only if, but let me write it just in this form. And it's sufficient to write down this equation, to solve these equations. Yeah, let me not write like this. So G phi eta with eta pure satisfies the Killing-Spinor equations if and only if the following two conditions are satisfied. The first one is very simple. It's just the fact that L is a Lie algebra. It's involutivity for L. And the second one is a bit more interesting. It tells you that if you take any isotropic basis, epsilon j bar from j1 to n, we satisfy that epsilon j, epsilon bar k is delta jk. Then the following object, the following quantity, the sum from j1 up to n of epsilon j bar, this is well defined, it is independent of the basis. You can do this calculation simply, is minus j eta phi plus. And phi plus here is the projection into plus of the divergence. Okay, so this is a very handy expression. So we have a physicist who will tell you that these equations are some sort of integrability conditions. We know that. I mean, it's some closing of the bracket. And they will also tell you that in this setup, this equation should be some sort of moment map equation. And this is what we are going to prove now. So I claim that this equation is a moment map condition, at least when there is no divergence. And what this will imply is that the moduli space of solutions of the Killing-Spinor equations has a special metric, or at least a symplectic structure. So consider the space L. Now I changed my parameters because this thing is not very useful, but I consider the space of subspaces of G complexified such that the dimension of L is n. They intersect trivially with the conjugate. So they define complex structures on L plus L bar. And when I restrict the pairing to L plus L bar, this is non-degenerate. So in particular, if I restrict to the real points of this, it will give me a metric. Yeah.
So you don't know phi pluses. Phi is just any linear function.
Yeah, phi is just an element here, is just an element in G or G dual. And the phi plus is the projection into plus with respect to the generalized metric. So I have G. G is acting on the quadratic Lie algebra, and it decomposes as a plus minus. Here G acts as an identity, here G acts as minus identity. And I have my phi, which I identify with an element in G using the ambient pairing, and this has a plus part and a minus part. Okay. So firstly, it's a simple observation that just by definition, this is a complex space, right? This is just a subspace of some Grassmannian inside the Grassmannian of n planes in G tensor C. So this is a complex manifold. Yeah. So what is the tangent space? the tangent at a subspace L of L can be identified with the homomorphisms from L into L bar plus B minus tensor C, where B minus is defined in this context as the orthogonal with respect to the metric on G tensor C of L plus L bar. And this is well defined and has the right dimension because we are assuming that this is non-degenerate. So therefore, this is a complex manifold, just multiplication by I is the complex structure. And I have even holomorphic coordinates. Because if I choose an L, nearby I can express any L as a graph using these objects. Right? So I have natural coordinates. And now if you give me a tangent vector in here, then I can decompose it in two bits. This bit is taking L to L bar, so it's just a deformation of the complex structure that I have on L plus L bar. I want to think of this J dot as something real, so I'm going to identify with an endomorphism from B plus to B plus, where B plus is the real points of L plus L bar. Which anti-commute with the given J. At the point where I am, L plus L bar has a natural complex structure, so B plus has a natural complex structure, and this guy, because this is taking L to L bar, it anti-commutes. Square equals minus J plus J dot equals to 0. And similarly, this J dot, I can think of it as an homomorphism from L to B minus tensor C. So the dot, the G dot, I want to also think of it as real. My J dot is going to be now an homomorphism. I mean, as a complex homomorphism, we think of it as going from L to B minus tensor C, but I want to take the real part, so it's going to go to L plus L bar to B minus. So it's an homomorphism from B plus to B minus plus an homomorphism from B minus to B plus. Okay, so now I can write down a symplectic structure and state the results. So the proposition, this is this was proved by a master student in Madrid, Juanjo Romero, some years ago, is that, I mean, the symplectic part, the complex part is kind of not too difficult. But L has a pseudo-Keller structure I mean, if you don't know what pseudo-Keller is, no problem. Just have to think that it is symplectic, it is complex. The symplectic structure is of type 1-1, and the corresponding symmetric tensor may have indefinite signature. Okay? It has a pseudo-Keller structure preserved by the G action and there is a moment map which is precisely given by the following. So from L to G dual, you take an L and associate the contraction with the ambient pairing on G of I have sum from j equals 1 up to n of epsilon j bar, which is this quantity which appears here. Okay? So the proof of this is some calculation, but essentially amounts to identify what is the right symplectic structure in this space. And the symplectic structure, I can just write it out for you, is the trace on B plus of j2 dot j1 dot minus trace on B plus of j2 dot j1 dot. So I take variations of my L. It gives me this j dot and this j dot and g dot. And you can check that this quantity is actually a symplectic structure and of the right type. So if you know Keller geometry, this is the natural symplectic structure in the space of complex structures on a manifold. This was discovered by Fujiki some time ago, I guess. Okay, so I would like to state a theorem, but I can't. I'm going to state a problem. It's not an exercise. It's more difficult than an exercise. And the problem is to prove that the modular space of solutions of the Killing-Spinner equations is actually a pseudo-Keller manifold. So problem, prove that the modular space of solutions of the Killing-Spinner equations in this setup with eta pure modulo the action of G is a pseudo-Keller manifold. It's actually more. It should be of Hodge type. It should have a pre-quantization on top. So it's ready for quantizing it. It's a pseudo-Keller manifold. And the reason why I cannot give you a proof of this is because in the Keller setup, when the associated metric is positive definite, there is a very well-developed machinery for constructing Keller reduction. You do symplectic reduction, and then you prove that the complex structure also makes sense, and everything is nice. In the pseudo-Keller setup, things are much more complicated because certainly you can do symplectic reduction, so this is going to be symplectic, away from the singularities, but the complex structure may not descend, because you may have some directions for the action of the Lie algebra G, which are null vectors, and then things may degenerate. This is the first complication. So this is the first difficulty is the pseudo-Kellerness. The second difficulty is much more interesting and has to do with the fact that the Killing-Spinner equations are not zeros of a moment map. There's this weird term on the right. And I don't know if there is a theory which explains this. I believe this has to do with this machinery about shifted symplectic structures that Daniel Alvarez is developing with Enrique Bernstein and Miquel Cueca. Because when you go to the geometric setup and do the same construction, this G gets promoted to a L infinity algebra. And then you have to do some funny things which are not standard. And I believe that your machinery should be the right place for understanding this, but I don't know. Okay, so shifted symplectic stuff, I have no idea. This is related to the fact that these are not zeros of a moment map. And what we have done in the geometric setup is to do some sort of reduction by stages. But this reduction by stages does not fit into the usual box of symplectic reduction by stages. So there is something funny. Okay. So maybe it's a good time to give you an example. Okay? A very simple example where you can see that this is happening nicely. Now I can give you an example. And the example is very simple. It's just you're going to take the group SU2 cross U1. Okay, so this is topologically, this is just the 3-sphere cross the circle. And I'm going to take this double quadratic Lie algebra. K plus K dual with a pairing given by duality. In my presentation, I don't know if I want to, I mean, there is some, I can't tell you what my notation is, but it doesn't matter. Here you have generators B1, B2, B3, and these are generators of the SL2, of the SU2, and then here you have another generator which is B4. So for example, in my notation, B2, B3 is minus B1. I can write them all. B3, B1 is minus B2, and B1, B2 is minus B3. So I can take here a 3 form on the group, which is just given by the Cartan 3 form, but modified by a parameter L. So this is just L times B1, 2, 3. And I consider the natural bracket twisted by this H on G. So choose two parameters XA which are positive and define the following metric GXA to be A over X sum from J equals to 1 up to 3 of Bj tensor 2 plus x squared B4. This defines a generalized metric with B plus given by x plus gxa inside G. And this has, I can define a natural complex structure in here, which is like a complex pure spinor, which is defined as follows. Ix on B4 is, so here I identify B plus with K by projection. So this is a graph. So Ix of B4 is B1 with some correction, so it's minus, is XB1. Ix of B2 is B3. And I furthermore choose a divergence which is of the form phi equals minus x B4. Now this is an exercise. The exercise now is to prove that there is a specific value of L for which this is a solution of the Killing-Spinor equations, meaning this thing. So exercise, if L equals A over X, then this solves. This is a solution of Killing-Spinor equations. And of course, I encourage you to use this formulation, because if you go for the spinor, you have to do the work that we did in the paper of writing it in terms of this form. Okay, but this is very, very simple. And furthermore, and this is going to be important for later, this divergence is special because its plus part preserves L. And we call this a holomorphic divergence. And it's going to play a role in the construction of vertex algebra representations. Okay, so we have a nice example. what about the problem that I formulated there? Well, the A parameter, I mean, you can really do this also for the X parameter, but let me say that the A parameter is naturally complexified by considering a B field. My generalist metric I have written down without the B field. It only has the metric. It's naturally complexified by a B field of type 1-1. Complexified by the following B field, depending on another parameter y, and this is 2, 3. You can check that this is of type 1-1. And so you can regard this as the complex, the coordinate y plus ia as the complex coordinate that we had in the space of calligraphic Ls before. And now there is a natural functional v, which is log of omega xa squared. This is the natural Hermitian form associated to this metric and this complex structure, divided by the standard volume 1, 2, 3, 4. You can write this explicitly. This is just log of A. And guess what? If I do DDC of this, it just gives me the hyperbolic metric in the upper half plane. So I dd bar V is the hyperbolic metric, which should correspond to the metric on the moduli space on the upper half plane. So this is one example where everything works nicely. I still have 10 minutes. Okay. Do you have any questions about this? I mean, so if you want to know more about which type of a structure we can expect in the moduli space of solutions of the scaling experiment equations, Arpan Saha was presenting a poster. Where is Arpan? Okay. Arpan was presenting a poster yesterday or the day before, and you will give a talk in a geometric situation, but it's actually related to this fact. And at least these manifolds and these moduli spaces should have a very rich geometry, at least in the case that the dimension of V plus is even dimensional. Okay, so to finish, I would like to consider another situation, another example, which is for Andrew, sorry. This is the case that the dimension of V plus is 7. Okay. So what happens with the Killing experiment equations if the dimension of V plus is 7? So another, well, this will be like 1.5 or 1.4, I don't know, is the case that the dimension of V plus is 7. And this relates to G2 geometry. So in this case, now I take a real spinor non-vanishing on B plus is equivalent to a positive 3-4 on B plus. To phi, a 3-4 on B plus. We satisfy some sort of positivity condition. I can explain this very easily in words. So this is 7-dimensional. So the space of 3 forms has an action of G LR7. And by dimensional reasons, it turns out that there is an open space here, which is an orbit for the GLR7 action. And a positive 3 form is any point in this open orbit here. So firstly, how do you relate the spinor to the form? There is a formula. So the space of spinors in this case can be identified with R8 with the Euclidean metric, and is decomposed as R7 plus R eta. And from the spinor this has a natural pairing, and from the spinor you can recover the form x, y, z is Clifford multiplication, Clifford multiplication, Clifford multiplication, eta, eta. And a more explicit way of writing the free form, so there is always a change of frame, so that you can put the free form in this form. So the way of remembering how these free forms are is take B1, B7, and think of this as R6 plus R. In R6, I have a natural SU3 structure. So I can write down the Hermitian form or the symplectic form of the SU3 structure. So this is B12 plus B34 plus B56. And I wedge this with B7. And I have to add another part, which is the real or imaginary, depending on your convention, the real part of the complex 3 form, which is B1 plus IB2, which B3 plus IB4, which B5 plus IB6. So this is another way of explicitly describing this thing. And yeah, all I want to tell you about this is just an example of solution of the Killing-Spinor equation. In this case, there is no such nice formulation of the Killing-Spinor equations. Essentially what happens is the group G2, which is the stabilizer of this 3 form inside GLR7, is also the stabilizer of the spinor inside the spinor representation. And you can write down the equations for the Killing-Spinor equation as suitable parts in lambda 2 lying in the algebra of G2. But it's not very likely. I mean, the example, which is exercise for you, is to check either by geometric means or by algebraic means that the following is an example of solution. So take K equals SU2 plus SU2 plus R, and take G to be K plus K dual as before. I'm going to take here vectors 1, 2, 3, and here vectors 4, 5, 6, and here V7. And then I take 2 parameters, and I define the following 3 form on K, which is S B1, 2, 3, so the Cartan in the first SU2, plus L B4, 5, 6. So this defines a quadratic Lie algebra structure on G with a pairing given by duality. And now my claim is that if I define phi to be omega wedge eta plus omega plus, where eta is here some other parameter which is real, it's a square root of T divided by L V7. Omega is a square root of SL V14 plus V25 minus V36. And then omega plus is the following combination, is a square root of S cube B123 plus L square root of S B156 minus L square root of S V2 4, 6 minus L square root of S. V 3, 4, 5. This defines, associated to phi, there is a natural metric. You can calculate it via some standard formula. I can tell you the details, but the point is that the exercise is to prove that this is a solution of some deformed version of the Killing-Spinner equations. Solution of the Gravitino equation is satisfied, and the Dilatino equation is satisfied up to a scalar, lambda, and this lambda is geometric. It's related to one of the torsion classes of the G2 structure. So this lambda is given by 7/12 tau naught, where if I think of this geometrically as a 3-form on the group, this appears when I take d phi as tau 0. This is tau 0 star of phi plus ... So the 4 forms decompose as irreducible representations for G2, and this is the one-dimensional component. Okay, so I finish here, and thank you for your attention.